All right, guys. So we're into week 3. Same setup as last week. The lab is due on Friday. I messed up and put some different dates and confused some certain people with the lab for last week. So you are also able to turn in the lab for last week this week. But I'll try not to mess up going forward, and let's just all stay. So every week the lab will be due on Friday. And then you have another 5 days to do the homework. So I'll get you thinking about thermodynamics all week long. All right.
I checked the calendar. Is there a lab due this Friday? So I didn't see it up there.
I thought I did. I swear there is. Let me look. Keep me honest. See, this is week 3. Lab. It will be available. What should we do? It says due date 1/22, 2021. That's Friday, right? Yeah. Worth 100 points. Display after 120. 2021. You probably don't see it until it pops up, until it's displayed.
Yeah, that's what's going on. I'm seeing homework 3, but not lab 3. So I'm assuming it's just because it hasn't been public yet.
Yeah, I don't. I'll remove that stupid display thing. There you go. Here we go. Submit. All right. Okay, so we've already talked a little bit about homework questions. Anybody else have any other questions? Okay. We'll talk more about thermodynamic systems and processes. Then we're going to talk about phase change. So I'm hoping that all of this information begins to bring the information together for what you have been learning about thus far in this class. So we're looking from page 26 to 30. There are a lot of systems here to define, as you can see. Isolated, closed, open, the surroundings, equilibrium, constant volume, steady state. And there's many processes that we're going to define. Now, this is a lot of information, but it's good stuff to understand. And this is stuff that we will be tested on. So there are basically 3 types of thermodynamic systems. An isolated system is not in any way influenced by the surroundings. Now, is there really any such thing in the world thermally that's not influenced by its surroundings? No, there's no such thing. Okay? But in order for us, the influence for certain systems might be so minute and small that we can ignore them. Therefore, we can call it an isolated system. It's a way for us engineers to keep things as simple as possible when we're dealing with complex systems. And just remember, it's not influenced by any of the surroundings. There will be other definitions that you will see in here later on in the term, especially when we start studying the first law of thermodynamics, of how else you can explain and look at an isolated system. But this is one thing you know about an isolated system. That is one that is not influenced in any way by its surroundings. That's how we look at it. Then there's a closed system. It has no transfer of mass with its surroundings, but may transfer energy. Now, These type of systems do a lot of work. I'm sure you can think of a few if you really think about it. It does not transfer mass, but it transfers energy. Okay. And then an open system is one that transfers both mass and energy with its surroundings. Isolated, closed, and open. So let me hear from one of you. Give me an example of an isolated system.
That one almost seems like it might be the hardest one.
Yeah, well, okay, give me an example of a system that you would consider isolated.
Maybe like a cooling system for like a computer or something, like a water cooling.
Water cooling. Okay. Yeah, these are the type of discussions I want to have. It almost is, but the water cooling system transfers one thing, right?
Yeah, the heat from
And
the CPU can
yeah, so
transfer
that
it into
would
the
be a
water.
closed.
That would be
That
closed.
one would be closed.
All right. Let's see.
So not an isolated system, but would a car engine be a closed system?
Yes.
Or is I was gonna think the only thing I could think is the kind of like after product
Mhm.
created in the exhaust. I don't know if that would consider it an open, but it's only really going one way.
An open system now that can be very much argued. It depends. So, like if you have the car itself, let's say we have the whole car, and please don't mind my art. And here's the engine, right? If we have a whole car, this engine gets gas from here, right? And then that gas goes into here and it makes the pistons turn and it makes your wheels turn. And then it exhausts air out into the environment right here, right? So if you're looking at this system from this perspective, meaning like the whole, your boundary condition for what you're analyzing the system, then yes, it's an open system. But if you're looking at it from this perspective, like I just want to see, I want to know what goes in the engine and what comes out the engine, then it's a closed system. You can look at it, you can analyze it as both. It's just, it really shows you the reason why we have these thermodynamic systems because it just gives us a way to make the problem simpler.
It's kind
So,
of a easy way to understand what's happening.
exactly right. So, let's say let's say you're analyzing the the engine here and you don't want to know anything about the radiator, but you know the radiator cools the engine, right? You can say that radiator is a closed system and you just want to see how much energy comes out of the engine, how much heat. And then you'll go and analyze the radiator and say the radiator needs to be this size based upon the amount of energy that the engine expels. You see what I mean? So like there's really not truly an isolated system, but isolated systems come in handy when you're trying to analyze thermodynamic systems.
It's almost like context plays a big role in kind of figuring out which kind of part is a closed system or an open system on something like a car.
Oh yeah, there's so many there's thousands of subsystems inside of a car that you can look at from a that they do look at from a thermodynamic process. What's a good big open system that everybody is very their comfort is provided to them by?
An air conditioning unit.
That's right. HVAC, air conditioning. It's huge open system. Huge open system. Salman, I'm teaching a class right now.
So why would the AC be open? It consider like what is the air it's moving considered the mass?
Air has mass. Yes, it does.
Okay, so I just wanted to make sure that's what I was.
Yeah. Air has mass. You know, there's 14.7 pounds of pressure sitting on every square inch of your body right now. And if the pressure went to zero, you would explode. It wouldn't be any good for you. The cells and molecules in your body will start doing weird things. So air has mass. Yes. We're like fish in the bottom of an air ocean. If you took us out of the air, we wouldn't know what to do, right? All right. This is more stuff about thermodynamic systems. So, thermodynamic equilibrium, when a system is in equilibrium with regards to possible changes in state, it's when the system is in equilibrium. For example, if my room temperature is 72 degrees and my thermostat setting is 72 degrees, right now that room is in equilibrium because the system, if you consider the HVAC, the system to feed the room, and you consider its feedback, the temperature sensor on the thermostat, once it reaches 72 degrees and it's in equilibrium with the system. But is it so? If you think about that room, that 72-degree room, and the room next door to it is at 65 degrees, there's no equilibrium, right? So then there's heat transfer. Heat always travels from hot to cold. And that's going to be another law, thermodynamic law that we're going to learn about. So another thing is a control volume. So the control volume is a fixed region in space for you to study the thermodynamics. Now that's exactly what I was showing you back here is the car. This little dotted line, this is my control volume. I was saying, hey, I'm just going to look at the engine. That's my control volume. So all energy into this box and all energy out of this box is how I would analyze that engine. Now, if I wanted to just look at the wheel, I draw a control volume around the wheel and figure out what type of energy goes in and out of that wheel. Now, you may think there's no energy going in and out of that wheel, but there's definitely friction, heat loss, sun hitting the black wheels. There's so many things. So I do a control volume on that wheel, and you can do a thermodynamic analysis on that wheel to see the hot and cold going into that wheel at a certain time of day um, or other predefined assumptions you might make. No. So steady state is a circumstance where there is no accumulation of mass within the control volume. The system is independent of time. So how can I explain this one? So this is like, let's say, okay, let's say we have a tube. Let's say this tube, this little line right here that I'm drawing is a 5 millimeter diameter tube, a glass tube that goes like this, and then it spits out. It's a tube. And let's say we pour water into the tube, and then water comes out of the tube. So let's say this tube takes 5 seconds to start 5 seconds to start water leaving from the bottom end. I know that's not proper English. Tell me if you don't understand. For water to begin leaving the bottom of the tube. There we go. Do we understand?
Yeah, basically takes 5 seconds for any water entering the tube to reach the end of the tube.
Right. Tube. So 7 seconds into the us pouring the water into the tube and the water leaving out of the tube, and let's say we draw a control volume around that, is that system for that control volume I just drew the dotted line around for the tube in steady state 7 seconds later?
It seems to be.
Yeah.
At
Yeah.
that point, there's no more water that can really be in the system because it's kind of at like 100% of the water in the tube. So as long as you keep pouring, it kind of stays at that same state.
Exactly. So that's steady state. That's it in a nutshell. Now, at 3 seconds, is the water at steady state?
No, because it hasn't reached the bottom yet.
Exactly. That we're in what we would call transient phase, and that's like thermodynamics 2.0 later on. But right now, most of the systems that we will be analyzing and the systems that I analyze today, we look at them from a steady state perspective, meaning that they're not starting up, there's no starting phase. We're saying this thing is operating in steady state. That steady state concept that we just looked at, the water going through the tube and taking 5 seconds to get to the bottom, most systems, when you analyze them, you're looking at it after those 5 seconds. You're saying everything's flowing and it's running. It just gives us a way to make it simpler. All right. So here are some more thermodynamic processes. So whenever a property of a system changes, a change in the state of the system occurs. So what's a property? You'll understand that more later. We're talking about properties. We looked at specific enthalpy, specific volume, specific internal energy, specific energy. Those are all properties of a system. So here are just some of the processes that systems are categorized as. So when a system in a given initial state goes through a number of different changes in state and finally returns to the initial values, the system undergoes a cyclic process. Cyclic process would be a radiator in a car. That fluid really never changes, right? All it does is take heat and dumps it to the environment, right? It takes heat from the engine, puts it in front of your car, then in front of your car blows cold air through the radiator to cool off that radiator fluid, and that radiator fluid goes back through the engine to take more heat away from the engine. Okay, so that's a cyclic process, which is I deal with those all the time. I mean, refrigeration, most heating, steam, heating loops, things like that are all cyclic processes. Now, a reversible process is for a system that is defined as a process that once have taken place can be reversed. So doing leaves no change in either system or surroundings. Now, there's no such thing as a truly reversible process ever, ever, ever. entropy makes that so. The law of entropy says there's no such thing as a truly reversible process. So you might ask, why do we look at processes as reversible? Well, the simple answer is so we don't have to deal with entropy. But the a better answer is to analyze the system as if it's a perfect system, and then we will deal with the imperfections later on. So, are there any questions about that? It's kind of a head scratcher. There's no such thing as a reversible process.
Less a question and more just making sure I'm making sense of it. Basically, we use the idea of a reversible process not because we can actually reverse it perfectly, but almost treating it like we can reverse it perfectly is, and then dealing with the minor issues after the fact is easier than trying to quantify those minor issues in the actual reversible process.
Correct. Yes. It's a way to do it. It adds a lot more value to analyze it without thinking about the imperfections in the system, because the only reason why there's nothing is reversible is because entropy, and that means that everything is always going to a state of being more random. It's This is a very hard concept to explain myself. So it's really imperfections, friction, for example. So instead of doing all the quantification and all of the process to really understand friction losses, much of the time, and we look at reverse processes as reversible, so we have to deal with the friction. In one way that you can look at that, processes are not perfect and are always irreversible is we'll go back to our radiator example. Why do we need to fill up the radiator fluid every so often if it's a fluid that goes in a cyclic process, and it is supposed to be a closed, isolated system that does not have any interaction with the environment it's in?
I mean, I don't know the exact reasons why, but I know that I mean, on a basic level, it's probably just because through being used so often, a bunch of really minor, tiny little things, like due to friction, like you're talking about, could
Yeah.
cause the fluid to become less effective.
Yes, it becomes less effective, and that's all because of entropy. All of that is because of entropy. Entropy, not enthalpy, entropy. So an irreversible process is the opposite, in which is really what all processes really are. Because to go back to the breaking down of radiator fluid, if a process was truly reversible, then the radiator fluid would not break down. Can you put radiator fluid back together after it breaks down? You can't, without
No.
putting more energy into that radiator fluid to reprocess it and do all the chemical stuff that you have to do in order to get it to be a viable radiator fluid again. So it's always irreversible. Everything is always tending toward a more random. I mean, there's whole books about entropy, and you still won't get it. So, all right, now irreversible. We just talked about that. Opposite of reversible, and usually is what the system is looked at. But a lot of the processes we will look at it will be a reversible process. This will be, hint, hint. This will be an assumption that you make. You know, you might say, "Hey, it's cyclic process and it's reversible." I'm assuming it's reversible. Because if you don't assume that it's reversible, then I'm going to be like, well, where's the entropy and the heat loss, and where's this and where's that? All right. So here, this is just talking about some of the things that we were discussing. What causes what causes irreversible processes? Friction, just like our radiator example. Unrestrained expansion of fluids happens in radiator too. Heat transfer through a finite temperature difference. This is impossible to stop if you really think about this. A finite temperature difference. That means a measurable temperature difference, right? If you take, there's a temperature difference for everything. So it seems that everything that we do is always an irreversible process because there's always a temperature difference in everything that we do. And then mixing of two substances, you know, when you mix two substances and you go through a chemical reaction, how easy is it to unmix those two substances? It's not, you can't do it, right? Without putting some type of energy into the process and making it equal. So I just need to make sure you guys know what I mean. Like when I say energy, so if a process takes 10 BT, if let's say I mix two substances, S1 and S2, and they both go to this substance, S1 plus 2, and then it gives off, this is the heat it gives off, and this is equal to 20,000 BTUs. Okay? I guarantee, like, I bet my life savings that it takes more than 20,000 BTUs to separate these substances back into S1 and S2. There's a way to do it, I'm sure, but it always takes more to get it back to the initial state. Therefore, the process is irreversible. If it takes more energy to get it back to its original state, it's an irreversible process. All right. An adiabatic process. You're going to hear this is a cool word that, you know, I remember from my class. It's one which is there's no heat transfer in or out of the system. The system can be considered to be perfectly insulated. Now, is there any such thing as an adiabatic system where heat is not transferred in and out of the system? No, there's no such thing, but it's part of that reversibility concept. It's part of the concept. I am not considering the heat right now. This process is adiabatic. I'm not considering its surroundings or anything. It's perfectly insulated from everything. Are there any questions about that? All right. Isentropic process is one which the entropy of the fluid remains constant. This will be true if the process system goes through is reversible and adiabatic. So an isentropic process has to be reversible and has to be adiabatic. It can also be called a constant entropy process. Now, okay, so I just said in order to equal isentropic, if it equals isentropic, then it's equal to reversible, and then it's being adiabatic. Now, here's a question. Does an adiabatic process have to be isentropic?
I don't think so.
Okay,
No, 'cause it can be irreversible.
say that
It can
again.
be- I said no because it can be adiabatic and irreversible, and then it wouldn't be isentropic, right?
Yeah, that's very true. It can be an adiabatic and irreversible. Exactly. So let me finish writing this. So okay, process have to be adiabatic to be isentropic, and we have said no. And we said no, and you're saying it's because it can be irreversible and adiabatic, right? So give me so here this might be a little bit too much, but I'll give this one to you. So like let's say that we have an engine and it turns a piston. We have a motor and it turns a fan. And we're not even looking at this fan. We're looking at this right here, and we're looking at the 3 leads of electricity going into the fan, right? And then we're thinking about the energy coming in to the motor, and then we're looking at the this right here, the actual motor turning, right? So we know that the motor turning is uh, the motor turning and the electricity is not a reversible process. I cannot turn the motor and put the amount of electricity back into the wires that the wires have supplied to the motor. But I can consider this process adiabatic in saying the temperature here is the same as the temperature here. Temp. So because adiabatic, we're saying that there's no heat transfer in or out of the system. So we're saying no heat transfer. So we're saying, hey, this system up here, we're just looking at it for the electricity. We're just looking at it for the electricity and the mechanical energy it produces. We're saying that the heat does not matter. It's an adiabatic process. You see how that can be useful? Like we don't even care about the heat right now. We're just looking at the electrical energy coming in and we're looking at the mechanical energy coming out. But it's not isentropic, right? Because like I said, it's irreversible. So it's not a constant entropy process. Polytropic. When a gas undergoes a reversible process in which there's heat transfer, the process frequently takes place in such manner that a plot of the log pressure versus log volume is a straight line, or stated in an equation, PV to the n equals a constant. I know you guys seen this, PV to the n equals a constant because you did the homework one. So this type of process is polytropic. And poly is the expansion of a combustible gas in the cylinder of water cooled in a reciprocating engine. So, all right, it's reversible when a gas undergoes a reversible process. So water turns from liquid state to gaseous state, and it can turn to a solid state as well. So it's reversible. So that's polytropic process. Does a gas engine go through a polytropic process? Does the gas cause the engine to be polytropic?
No, because you can't reverse what happens after.
Exactly. You cannot, after you combustion the gas, you can't put it back together, right?
Right.
Right. So this PV to the N process would not be constant. So the PV to the N the PV to the N is constant only in a polytropic process. Only when there's a solid relationship between pressure and volume. All right, on to the next one. I keep doing that. All right. All right. Throttling process. Now, this is just here for you guys to know. We're not going to deal with throttling processes that much, but I can go through it real quick. So, it's defined in which there's no change in enthalpy, like there's no change in energy. No work is done. Work equals zero. Okay. Process is also adiabatic. So, we're saying no heat is transferred to its surrounding. So, Q equals zero. So, to understand it, let's go through an example. So, an ideal gas flows through a valve in its mid position. From experience, we can observe that pressure in is greater than pressure out, and velocity in is less than velocity out. So where P equals pressure and VEL equals velocity. These observations confirm the theory that HIN, which is enthalpy in, is equal to enthalpy out. Why? Because remember, H equals the internal energy plus the PV energy. So if pressure decreases, then specific volume must increase if enthalpy is to remain constant. And we are assuming that the internal energy in whatever ideal gas is constant. So since mass flow is constant, the change in specific volume is observed as an increase in gas velocity, and this is verified by our observations. The theory also states that work equals zero. So no work was done. It just changed in its specific volume, and that change in specific volume was compensated by the change in velocity and pressure. Finally, the theory states that an ideal throttling process is adiabatic. This cannot clearly be proven by observation since a real throttling process is not ideal and will have some heat transfer. But this is the basic way that we analyze throttling processes. We'll look at it where Q equals zero, so it's adiabatic, and we're saying zero work is done. So we're saying, oh, it's a throttling process. And H1 must equal H2. So that relationship here, P times V, must stay the same. It must be constant, right? So pressure and volume can change, but they're what they equal in the last thing that we talked about, which is PV to the N equals is constant, must remain the same in order for a throttling process to be true. To be like really considered a throttling process. So that again makes it easier for us to analyze the system by considering it. Hey, this is the throttling process. No heat transfer to the surroundings and no work is being done. H1 is equal to H2. Then you can analyze this system because you know these relationships. Thermodynamics is all about knowing the relationships. All right, change of phase. Page 31 through 39. So before we go on to change of phase, we can take a little talk if you guys want to talk. I threw a lot of information at you, a lot of definitions, a lot of processes. I mean, like your head might be spinning right now. So If you don't have any questions, I understand. But if you have some questions, I'll happily go back and try to explain better. Ted's gonna-
I'm personally good. There's definitely some stuff that might be a little more intense, but it seems like once we do the homework, it might become a little more clear. But I'll let someone else ask in case I need to.
You guys good? Feel free to ask, man. We're all trying to learn here.
Oh, I'm good.
I'm
Okay.
good.
All right. Okay. So now we're going to start looking at phases. What is a phase? A phase is different. A phase is what a liquid. So there's three phases of water. There's liquid, there's gas, and there's solid. Right? Solid is water is a working fluid that we use often. So now there have been tables generated for different types of substances that we can use in order to tell what phase that liquid or solid or gas is in, if it is a liquid, solid, or gas. And guess what those properties might be that we can use to tell what phase a substance is in? They're specific. No answer?
Like specific heat or
Yeah,
specific volume.
yes, yes. If you know two of those properties about a substance, you can find everything else about that substance. Two of those specific properties. Okay? That is why these specific properties, the specific volume, specific heat, specific enthalpy, specific entropy, are very important, because those, and if you know that, two of those, or if you know pressure and the temperature in one of those, you can find out whatever you need to know about that substance in the process. You can find out if it's saturation, subcooled, superheated, critical point, triple point, its vapor pressure curve. You can find out the quality and the moisture content. These are all things that are in are classified within those three phases that I talked about: liquid, gas, and solid. And there's a plasma phase too, but I'm not really going to go that far. So we're going to distinguish between intensive and extensive properties. The intensive, what are these? These are the specific properties. And then we're going to describe some of these other processes, which is sublimation, vaporization, condensation, and fusion. All of these processes, you have forced water to go through at one point in time in your life. You just didn't know that you were making it vaporize or condense or fusion or even sublimation. Sublimation is the coolest one. You'll see why. All right. So classification of properties. We've been talking about this all term, but we can't talk about it enough. Intensive properties are independent of the amount of mass present. That's why we divide it by mass, because if we want to know the total of that intensive property, we multiply it by mass to find the extensive property from intensive properties. Extensive properties are a function of the amount of mass present, just like I said. So we'll do little v. What does that equal to? Feet squared divided by mass, right? So a function of mass. So to find big V is equal to little v times mass. And that is equal to, that will make you just have volume in this example. Does that make sense?
Yes.
All right. Intensive properties: pressure, temperature, density. And extensive properties can be converted into intensive properties by dividing by mass. It is so important for you to understand the difference between intensive and extensive properties in this class. Their intensive properties give you the information to find out the extensive properties. Then once you find out the extensive properties, you can find out how much work, how much heat, or how much anything is being done. But you can't do it without the intensive property. And here you'll get an example later on in this lecture, but it's important to show you the importance of the intensive property. And here's one. Here's a change of phase. So A, this is water. It's at 60 degrees and 14 psi. So B, it's that same piston. So it increases in specific volume and pressure is constant. So something must be added to it because of that. So heat must be added to it. And then in C, it says water at 212 degrees, specific volume is steady and uniform. So total volume extensive of C does not give us information about the substance. Why is that?
Is it because we have no mass?
We don't have, yeah, exactly. We don't know the mass. We don't, so
For all
let's
we know,
go
for all we
ahead.
know, it could be liquid water or water vapor. Since we don't know the mass and how much it weighs, all we know is the volume. It could be basically taken up by any phase of the water until we know the actual mass of the water.
Right, right. So let's just play like this here is irrelevant. We don't know any of this. And this here is irrelevant. This here is irrelevant, right? Right now, I'm going to ask you a question. If we knew the volume of this, is it possible for there to be 0.002 lbm mass pounds of water in there?
Yes, because it could just yeah, because it could be gas.
Exactly. Is it possible for there to be 1,000 lbm of water in there? 1,000 pounds of it? Well, water's about
If it was ice and it was enough ice to reach 1,000 pounds, definitely.
right, but we don't know anything else. Now, let's say we still don't know the mass, but we know the volume, right? We know the volume of this, okay? Now let's say we know the pressure. Can we find out what phase that water is in?
Yes.
Yeah.
We could, right? Because we could do all the math to see what pressure pounds per square inch is the water pushing on the outside. Then we can convert that into, yeah, then we can look at the PSI and we know the volume. Do we have enough though? I don't know. I think we need temperature. We know volume and pressure, but we'd also have to know temperature. If we knew temperature too, then there's tables we can go to figure out what is the mass of the water. So these two extensive properties, pressure and temperature, are two extensive properties that you can use to find out intensive properties. There's other ones too, but these are the major two, are pressure and temperature. All right, so now we're going to move on from the importance of understanding intensive properties using this example. And hopefully you'll remember one time while you're doing your homework, what's the importance of pressure and temperature. Now, we're going to look at the saturation vapor line. So saturation defines a condition in which a mixture of vapor and liquid can exist together at a given temperature. For example, water temperature or pressure is when a substance begins to boil. Water is 14.7 psi, which is atmospheric pressure at elevation 0 and 212 degrees. So at that pressure and temperature, water can exist at either a vapor or a liquid. So does that, have you ever noticed that even though your water is boiling, it's not completely vapor. You still can feel the moisture in the air and it still can touch you and make your hands wet because it's not all vapor. You breathe in water through your nose all the time, that's vapor. So for any pure substance, there's a well-defined relationship between pressure and temperature. So in this pressure and temperature curve here, and as you can see, this is the vapor pressure curve line. Above the curve, this is vapor up here. On the curve, right here, is both vapor and water and liquid. And below the curve is all liquid. So there's a pressure and temperature relationship for all pure substances that's pretty defined. And we have, as a human race, we have studied pretty much all of them that we know of. So now we're going to talk about the quality of that substance. And what is quality? So it's when the substance exists as a part liquid and a part vapor at saturation conditions. So saturation conditions for water is, here's saturation conditions for water. So even though what I'm talking about, we know that something along this line can equal a vapor and a liquid at the same time, we do not know the quality. QUA, quality. And what is the quality? Again, it's where is the quality is defined by the ratio of mass of the vapor to the total mass of both vapor and the liquid. Here. So if at 212 degrees, you're saying, okay, well, what part of it is vapor and what part of it is liquid? When we're thinking about gas, we're thinking about water. Well, you're talking about the quality. What percentage of that of control volume is vapor? And here, now realize these axes have changed significantly. Quality is used when a substance exists in the vapor dome. Okay? Now, what I mean by axes, notice that this one is temperature and this one is specific volume. Now, again, I'm going to go back to the other one. This one was pressure, and this one was temperature, right? So that's the relationship between pressure and temperature. But now I'm going to go back to the other one and say, all right, this is the relationship between temperature and specific volume. And here's where it's really going to kind of mess with you, is that this line here, okay, you see this dome right here? Notice it says saturated liquid, saturated gas. This line here, I'm going to star it. Is the same line as here. It's just looked at from different axes. Same line. This has a different characteristic, a different behavior because it's pressure and temperature. But when I go to this, now it doesn't want to change. Oh, there it goes. All right. Now I can see. I don't know what the heck happened. All right. So is everybody following me? This is a big jump. Are you following? You catching what I'm putting down? What's up?
Yeah,
Yeah?
just a different shape, right? I mean,
Yeah, yes, it's a different shape. But here, I'm gonna throw another thing at you. Now, this is called the vapor dome. Right here, this is what we call the vapor dome. And within this dome, substance can be a vapor or liquid. Okay? It can be a vapor or a liquid. So this is where you define your X. This X right here is defined by where is it at in the vapor dome. So it can be, it's very interesting, but now notice something else, how these pressures, these lines are straight in the vapor dome, right?
What does that mean? Like a constant pressure or something?
Yes, constant pressure. So the pressure may stay constant inside the vapor dome, and it depends on how the pressure. It depends on the specific volume of the substance in order for it to go into be a saturated gas, order to be in the gas part of the vapor dome or the liquid part. And we call this up here the critical point, where you're like superheated stuff that we're not really getting into above this. All right. You guys are going to get to play with some of this stuff too. So moisture content. Moisture content is the opposite of the vapor content of quality. So basically moisture equals 1 over quality, or moisture content is 1 minus X. So it's really just the opposite of what the vapor content is. So if a substance exists entirely as a vapor, as a saturated temperature, it's called saturated vapor. When a substance is completely a vapor, the quality of X is 100%. So if it's a complete vapor, the quality is 100%. You know, you might think, why do we call quality complete vapor? Well, it's because we use a lot of steam, and steam has the most quality, the most enthalpy in it when it's a complete vapor. We're going to be looking at these type of graphs for the rest of the term. You're going to get to know these graphs. PV graphs, TV graphs, you're going to see many different types of graphs. And you're going to look at a lot of different graphs and try to grasp how you use them. So we've talked about this moisture and vapor. Now we're going to talk about a little bit more about this temperature volume. I like to call it specific volume relationships. So we'll start here. So line A, B, C, D. So that means line A to B, B to C, C to D. Water at 14 psi, and then I put temperature at 212 degrees. How do I do that? Oh, it is. It's supposed to be temperature. I'm just telling you what it is. Okay, I need to correct that. My bad. All right, so water is at 14 psi at 212 degrees. So 14 psi, 212 degrees. As the volume, the specific volume goes up. I don't know why this should be specific volume. Volume doesn't matter. It's extensive. That was a mistake in the book. I'm sure of it. As the specific volume goes up, this is where the pressure line will be when you're talking about a temperature specific volume graph. So line EFGH is here. Goes the pressure as the pressure is 100 psi, so it takes a little bit more temperature to get it into the vapor dome. It rides the pressure line longer and stays in the vapor dome a little bit less time than it does in a pressure of 14.7 psi. And then same type of dynamics happen here from G to H. The line AJKL, same dynamics, but you know the right here though it's at 1,000 psi, so it's going to take longer to get into the vapor dome, a little bit longer, and the temperature has to increase drastically for it to get it there. And then it stays in the vapor dome less time, then it turns to a complete gas. Now, line MNO is 3,206 psi, no constant temperature variation process. So here, it goes directly from a liquid to a gas. This is the critical point. Point N is the critical point, inflection point, zero slope. So at this temperature, notice at M here, when the water is at 3,206 psi, the water will never go through a process to where it could be liquid and vapor at the same time. With it's either a liquid or it's a vapor. It's one or the other. When processes are above the critical point, the critical pressure, The substance deemed at a liquid if it's below the critical temperature, and a vapor when the substance is above the critical temperature. For water, the critical temperature is 705.47 degrees. Now, just to give you one last thing about this, and please read this chapter because it's very important, is line NJFB, NJFB. This is the saturated liquid line. In line NKGC, and what do I put? NKGB. What NKG? I was wrong. It's C. This is the saturated vapor line. So at this point, if we're right here, then X equals 100%. If I'm on the same pressure line and I go to here, X would equal 0%. That means the quality is 0. But the moisture content would be 100%. So M here, moisture content, would be 0. And M here, moisture would be 100%. For some substance within the vapor dome on that pressure. So other phases when heat is added. So now we get to talk about some of the other definitions. So when a substance changes from a solid to a liquid, i.e. ice is melting, the temperature, while the ice melts, the temperature remains constant. You never knew that, right? And what happens is the latent heat of fusion. So the temperature is remaining constant, but it's melting. But energy is still being taken away from the substance, from the water. So the latent heat of fusion is what happens when fusion happens, and it is the amount of energy, it's the extra amount of energy that it takes to melt the ice. So, and that's what is called the latent heat of fusion. Now, sublimation is when a substance changes from a solid directly to a vapor, no liquid state. There is a certain amount of energy you can put into water and it will instantly change from ice to vapor. And that's called sublimation. And that's why I think it's pretty cool. You'll just change ice straight to vapor. No liquid, no moisture content, no quality. It just goes straight to vapor. And then there's what we call the triple point. And this is when a substance can be a solid, a vapor, or a liquid. At this point, for water, the triple point is 32 degrees O2, 32 degrees F, and 0.08865 psia. So it's here. So this is just looking at other ways we look at phases and such. This is good to know. And yeah, so I'll just keep moving on, and that's it. That was a heavy chapter.
Oh yeah. Yeah.
Definitely gonna have to watch this lecture again.
Yeah.
All
same.
times.
Yep.
Yeah, that was a heavy chapter.
Luckily, we're recording.
Yes. Yeah. All right. I mean, Yeah, you guys are getting thermodynamics just shoved down your throat real quick in 9 weeks. So, welcome to the quarterly system.
Woo.
So, I mean, we have a few minutes. So, like, if you guys have any questions or anything like that.
I realized I had a question from the homework that I forgot to ask at the beginning of class.
Okay.
Yeah, I do
actually-
too.
Is specifically the question that talked about if you have like 15 pounds of steam. Hold on, let me pull it up. Someone wants to ask real quick. They can go
And
ahead.
then release 5 pounds of steam.
Yeah, the one thing, that one. I wasn't sure when you release the other 5 pounds of steam. It says you have 2,000 psi. My rationale tells me that would affect the psi releasing the 5 pounds of steam, but I wasn't sure how to quantify that in the problem or if you were supposed to. So I kind of just wrote the assumptions, and I'm assuming the pressure remains unchanged, but I know that it probably doesn't.
That's what I thought too.
Let me look at the homework. Exactly the question. Intro to thermo. We're talking about week 2, right? Homework, last week's
That would
homework.
be question 4 if I
Yep,
remember
question
correctly.
4 on homework 2.
Determine the PV energy, right? In 15-pound mass of steam at 1,000 psi.
Yes, that's the one.
Yeah, you got 1,000 psi, right?
Mm-hmm.
And then you're in 18 foot cube tank when 5 pounds of steam is released from the tank. The volume is still the same. What is the new specific PV energy of the steam left in the tank? All right, now this is kind of a double question, but what you have to do first, right, is first you need to know. Okay, I didn't say anything about the pressure. So yeah, this is a good question. It's pretty complex. So remember what we're talking about. We're talking about PV energy, right? We're talking about the pressure volume energy. And PV energy is pressure times volume, right?
Yes.
Okay, so the volume is 18 feet cubed, and you have 1,000 psi. You got to convert the 1,000 psi, right, to you got to convert the 1,000 psi to pounds per square foot, right? And then you can determine the foot pounds of the total system, right?
Oh, so it's almost just like missing a conversion where you just adjust the psi to actually be able to see what 5 pounds of steam being removed from the system would do to the psi.
Well, yeah. So it's what is the new specific PV energy? So yeah, that's a good way to look at it. So that's what I would do. I would convert it into convert the 1,000 psi into lbf per feet squared. Multiply that. So now I know what the total energy, the total PV energy in the system is, right?
Yes.
Yes. So then you know, okay, this is the total energy in the system. So then you can divide that total energy by 15-pound mass, and then you'll know what is the specific PV and specific PV energy for that system, for that steam. If you divide the total PV energy by the 15 pounds of mass, right?
Yes.
Okay. Now you have the specific PV energy. Now you've took 5 pounds out. Now multiply that specific PV energy times 10, and you'll get the total PV energy left in there.
So it's just changing the
okay.
15 to 10 and that's it.
The 15. Yeah, I guess you could. Yeah, you could do that too. Exactly. I know I do things a little like step by step. I start with the fundamentals, and I'm just looking at this problem again right now. So you guys, what you guys are gonna see is I found out that my best way to create homework problems is to create them, not solve them, and then solve them right before I correct the homework, so that I can always come back to the problem. And if I knew it was a bull crap problem, then then I'll give you some leeway. But if I can solve it when I come back to it, then I say, okay, it's a good problem.
All right. Well, it's
So
definitely I think you covered at least what I want. I might go back and do it again, but you might hear me bring it up again next class if I still have a couple questions on it or not.
yeah,
I think I got it now, but
yeah. Well, I mean,
definitely a question I'm gonna redo.
to play with the specific PV, determine the specific PV. Then 5 pounds of steam is released. The volume is still the same. What is the specific PV energy of the steam left in the tank?
For some reason, I got a higher PV after the loss than the original PV. Is that right? About right?
I don't know. I don't know. I don't. I think. I don't think it would be the. It would be high. It's specific. Oh, wait a minute. This is specific. So the specific energy in the tank would go down because now you only have 10 pounds. I need to do this problem, but it would. I need to think about it more. It's a good one though.
Oh yeah, it's that's the thing. The way you described how you do your homework, it sounds like you'll have our answer once you're able to get in there and grade it. So definitely, I would not mind a bit of feedback when you grade my assignment on that. That specific question is probably the one I would like the most feedback on.
Okay, I will. I will try to remember. If you hit it though, I probably won't give you much feedback. If you did a good job, I don't give much feedback. But if you didn't, I try to give you the piece where you kind of messed up a little bit.
Yeah, well, you'll definitely see where I had the same thing where my second value was greater than the first one, where it didn't seem like it should be. But
Yes, same here.
once you're able to grade it, I'll go back. I was planning on doing that problem over again after I had a chance to talk to you about it. And if I have any more questions, it sounds like next Wednesday we'll still be able to touch on it. So I'm not too worried.
Yeah, I'll grade it this Saturday. Wake up early in the morning like I always do, and hit them both.
All right, cool. Well, I've got a 10-year anniversary dinner to get to, so I will see you all later.
Congrats. Have fun.
Oh yeah, thank you very much.
Yeah, no problem.
Have a good day.
Yeah, you too. Hopefully, guys, see you next week. I know it's a lot, so you'll
Yeah,
have.
we'll see you later.
This video will be posted right after this, right?
I'm gonna post this video, so I have to process it. That takes like 20 minutes. So then in the morning when I get up and I start work, I throw it up there, and I'll throw up the answers to last week's what is it? Lab 2 and homework 1.
All right, sounds good.
All right.
All right.
I'll see you guys soon.
All right, you have a good night, man.
All right, you too. You too.
Bye, David.
All right, bye. Bye. See you later.